So me again, talking about some work we did on looking at national scale impacts of climate change on erosion and sediment loads. This is a collaboration with Ag Research and NIWA. So background, heard a lot of this in the previous talks, accelerated erosion and excess fine sediment has a lot of adverse effects on environment, social, cultural, economics. Estimated to have $100 million a year impact on pastoral productivity, or productivity in pastoral environments, and over 50% of our estuaries thought to exceed sediment thresholds for biotic impairment currently. And regional councils currently now required to manage fine sediment in river systems. But this begs the question of what's happening in the future. We've had some of that discussion. So how will erosion rates and sediment loads change in the future? Will there be a change in the relative contribution of these different erosion processes and sources of sediment? What mitigation approaches will we therefore need in the future to achieve the objectives we're looking at currently? And will those community objectives actually be feasible in the future? So this project looked at conducting Aotearoa's first national assessment of climate change impacts on catchment suspended sediment loads, producing projections for mid-century and late century, so about 2040 and 2090. To do that, we really needed to develop a national scale model framework that better recognises the contribution of different erosion processes to in-stream sediment loads and how those processes vary spatially across the country, as the models currently used at national scale do not differentiate by erosion process. They tend to look at total sediment load. And we also needed to bring in different climatic drivers for those erosion processes. So the currently used national scale models tend to only use mean annual rainfall as an input. So where that sediment comes from is going to vary spatially. In the soft rock hill country, we've got the shallow landsliding, as we've talked about earlier. And in the lowlands, we tend to have erosion from banks and superficial processes. So we first needed a spatial basis to partition sediment loads into these different erosion processes. And we account for these erosion domains based on the erosion terrains used in some of our other modelling. We've partitioned into five main categories. We've got the lowland terrain and the soft rock hill country, which tend to be dominant in the North Island. In the lowlands, we're going to get riverbank erosion and superficial erosion primarily, and soft rock hill country is going to be more dominated by mass movement erosion along with your superficial. And then we also have the hard rock hill country and mountain, which is more alpine type processes. So we developed this modelling framework. In the first component, we take two national scale models, NZAM, which models total sediment load, and Russell, which models superficial erosion only. And we use these two models through a process of differencing superficial erosion from total erosion to estimate the contribution from stream bank erosion in the lowland domains or mass movement in the soft rock hill country. So in those domains, we end up with total superficial load and an estimate of total mass movement or stream bank. In the hard rock and mountain terrains, we use NZAM only, as these are less susceptible shallow landsliding and those storm-driven processes, and loads are better estimated by mean annual rainfall and long-term erosion rates. We then have a component which looks at changes in the hydrological, hydroclimatic drivers of superficial erosion, mass movement, stream bank erosion. We'll use some modelling to look at percent changes in mean annual rainfall, storm rainfall, and mean annual flood in the future compared to the baseline. This gives us change factors in these hydrologic variables, which are then used to model future or estimate future sediment loads from our surface and bank erosion in the lowlands, so superficial erosion here, driven by changes in mean annual rainfall, and stream bank erosion driven by changes in mean annual flood. Soft rock hill country, we have again that change in superficial erosion, and we have a change in mass movement driven by a change in storm rainfall. And then hard rock hill country is driven by mean annual rainfall changes using enzyme. We then have a component which merges these loads, combines the loads at the watershed scale, and routes them through the REC2 river network, accounting for trapping or storage of sediment in lakes on the way up to the coast to give a total catchment load for baseline and future climate scenarios. For the climate scenarios, we look at 4 different forcings from the IPCC 5th assessment report. These have varying levels of CO2 concentration. We have RCP 8.5, which is sort of the worst case. We continue on the way we're going. We have 2 mitigation scenarios. We start to reduce greenhouse gas concentrations. It's RCP 4.5 and 6. And then we have a mitigation scenario where we actually start to decrease greenhouse gases. Each of these scenarios runs through 6 different global climate models. So these we use 6 models which are intended to capture the range of uncertainty in climate models. And these are downscaled from New Zealand using the New Zealand Regional Climate Model and referred to as RCMs. And using these 6 RCMs and 4 scenarios, we get estimates for 2040 and 2090 and the change in hydroclimatic drivers and therefore erosion loads relative to 1995 baseline year. In terms of the hydroclimatic drivers, we have change in temperature and change in mean annual rainfall produced from the New Zealand Regional Climate Model. Temperature increases across the country under all scenarios, and the biggest increases are under RCP 8.5. We have the highest greenhouse gas concentrations. The effect on mean annual rainfall and mean annual flood is more varied. We have east versus west effect of lower mean annual rainfall in the east, more in the west, and then higher rainfall in the south and drying up in the north. And that's most noticeable again under RCP 8.5 compared to the mitigation scenario. We also then get change in mean annual flood from the TopNet model, and that has quite a varied spatial pattern in increases or decreases, and some divergence, particularly in the South Island, between the different greenhouse gas scenarios. From the temperature, change in temperature, we estimate a change in storminess. So high temperatures, you're going to get larger and more frequent storms, and that's going to trigger shallow landsliding. So using enzyme, we model baseline suspended sediment yield using baseline climate and contemporary land cover. And then we use partition those loads into the different sources using the framework and look at what percent changes we get in future. So here I'm showing for 2090 between RCP 2.6 and 8.5. So these are the kind of end members of the results. What we see here is baseline high yields in the soft rock hill country. And those are the areas that really respond to climate change. With about 28% of the North Island potentially experiencing over 100% increases in yield by 2090 under this most extreme scenario. In the South Island, baseline highest yields in the Southern Alps will have a higher rainfall. In terms of the percent change, we get a lot more contrast between scenarios in the South Island, driven by the differences in the response of mean annual rainfall, mean annual flood, as we have a lower impact of shallow landsliding here. But we do, by 2090, see some of these soft rock hill country areas responding significantly by 2090 under the extreme scenario. The impact of that on suspended sediment loads, once we route that through the network, we see a much larger response by mid-century for the North Island, whereas a lower and similar response in the South Island across the RCPs. And then by end century, there's quite a large range in the North Island. We have anywhere from a 25 to a 115% increase in the sediment load delivered to the coast for the North Island, compared to the South Island, where we have anywhere from about a 6 to a 47% increase. And these bars are just showing the range across the 6 global climate models. So there's quite a range in responses that may occur. How that breaks down by erosion domain. You see in the North Island that soft rock hill country having a much larger range of response to climate change across the periods and across the different RCPs. The hard rock hill country has different responses across the North and South Island, primarily due to lower mean annual rainfall projected for the North Island compared to increasing for the South. And the lowland domains have quite a range in response across all scenarios, ranging from 50% increases to 50% decreases. So the key findings from this work is really that catchment characteristics play a really important role in how erosion and sediment loads are going to respond to climate change. And there's a lot of divergence in catchment responses, and that divergence increases with more warming scenarios. The relative contribution of erosion sources is likely to shift under projected climate change. So particularly in the North Island, we see that big response of soft rock hill country coming from a greater dominance of shallow landsliding and decreases in other processes. Lowland catchments are likely to have quite different responses across the scenarios, depending on how much hill country they have in their catchments and whereabouts they're located across the country. And coastal receiving environments, estuaries in the North Island may see much larger impacts than the South Island. We had ranges in regional loads between 1% in the South Island to 233% for some North Island regions. And this work has been published open access in geomorphology. If you're interested in reading more into it, you can download that with the QR code. Thank you.